We look at transformations of graphs in this video, and we'll talk about two types of transformations. The first one in this video will be focused on rigid transformations, and rigid transformations come from when we maintain the shape of the original function. We're just going to be moving that graph around. Essentially, it's like picking it up and moving it to a new location. A non-rigid transformation results in distorting the original shape of the graph. In this section, we will do these transformations to some basic classes of functions, and these you really should have committed to memory. So there's 7 of them. You should know the name of the function, the rule that defines it, what the graph looks like, and some properties about the graph, the domain, and range. The first of these is the identity function. It is the graph of y equals x. Remember that this is a linear function whose slope is 1 and the y-intercept is 0. So it goes through the origin with the up 1 over 1 for the slope. The squaring function is y equals x squared. Again, I can plug in values to figure out what happens, but 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4 are on that graph. The cubing function is y equals x cubed, so I will cube my input, 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8 are ordered pairs on that graph. The absolute value, y equals absolute value of x. So it's at 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. So it's that V-shaped graph. The square root function, remember we can't take the square root of a negative, so the domain is from 0 to infinity. 0, 0, the square root of 1 is 1, the square root of 4 is 2, so those are some order pairs on that graph. The cube root function, the cube root of 0 is 0, the cube root of 1 is 1, the cube root of negative 1 is negative 1, the cube root of 8 is 2, so we could plug in values to get the graph there. And then the reciprocal function, we'll talk about this one in a later section, but it is y is equal to 1 divided by x. Remember that we can't divide by 0, and so there is a break in the graph at x equals 0 because of that. In this first objective, we will vertically and horizontally shift graphs, and that comes from comparing the graph of a function, y equals f of x, to a new graph that's formed by y equals f of x plus k, y is equal to f of x minus k, and then we'll also look at f of the quantity x plus h and f of the quantity x minus h. So really when we have what I like to call an outside change and an inside change, and see how those changes impact the graph of the function. So we're first going to perform an activity just so you can visualize what's happening. We're going to graph y is equal to x squared, and then graph each of the 4 functions that I have listed and state how their graph compares to the original graph. We have y is equal to x squared plus 3, y equals x squared plus 1, y is equal to x squared minus 2, and y is equal to x squared minus 4. And I'm going to use Desmos to demonstrate these graphs. I'm using Desmos to graph the function f of x equals x squared, which is shown, and it is our basic parabola that has a vertex at 0, 0, and goes through points like 1, 1, and negative 1, 1, 2, 4, and negative 2, 4. We want to graph these other functions and see how their graphs compare to this graph of y equals x squared. I first want to graph f of x equals x squared plus 3. So whenever I turn on this graph, notice that f of x equals x squared plus 3 is a parabola. In fact, this is a rigid transformation. The shape has not changed, it's just moved to a different location. Note that on this one, my vertex is at the point 0, 3, and instead of going through the point 1, 1, my graph now goes through the point 1, 4, and also negative 1, 4. So note that each of the y values on that new graph is 3 more than the y values on the original graph. then f of x equals x squared plus 1, what do you think will happen here? When I graph it, notice that it's a parabola, but now my vertex is at the point 0, 1, not 0, 0. My graph goes through the point 1, 2, and negative 1, 2, rather than 1, 1, and negative 1, 1. So each of the y values on this graph is 1 more than the y value on the original graph. F of x equals x squared minus 2, when I graph it, notice that now the graph is down, right? It's shifting down 2 units from the original parabola that I had. Instead of going through the origin as a vertex, this new graph goes through 0, negative 2, and instead of going through 1, 1, it goes through 1, negative 1. So that y value has shifted down 2 units. And then when we look at f of x equals x squared minus 4, we see also that the parabola y equals x squared has shifted down 4 units. The vertex of this one is 0, negative 4. And instead of going through 2, 4, the new graph goes through 2, 0, and negative 2, 0. So those y values have all decreased by 4. And so when we have this outside change of plus or minus some number, our graph will shift up or down according to that number. So to summarize what we just saw in Desmos, the graph of y is equal to x squared plus 3 is the graph of y equals x squared shifted up 3 units. Y equals x squared plus 1 is the graph of y equals x squared shifted up 1 unit. Y equals x squared minus 2 is a graph of y equals x squared shifted down 2 units. And y equals x squared minus 4 is a graph of y equals x squared shifted down 4 units. So this outside change tells me how the graph will shift up or down. So I have an example. We have let f of x equal the absolute value of x, graph each function, and state how it relates to the graph of f. The first part is g of x, which equals f of x plus 2. We'll note that f of x plus 2 represents the function absolute value of x plus 2. Now by what we just saw, we know that this graph should shift the graph of f up 2 units. And let's just confirm that. We could certainly use our calculator, but I have a table of points. Notice that on my graph of f of x, I have the point 0, 0, 1, 1, 2, 2, negative 1, 1, and negative 2, 2 plotted, and then that V-shaped graph goes through those points. In my table I want to plug in the values of negative 2, negative 1, 0, 1, and 2 for x, and let's see what happens. When I plug those into g of x, I'm going to get the absolute value of negative 2 plus 2, which is really 2 plus 2, or 4. When I plug in negative 1, the absolute value of negative 1 plus 2 is 1 plus 2, or 3. The absolute value of 0 plus 2 is just 2. The absolute value of 1 plus 2 is 1 plus 2, or 3. And then lastly, the absolute value of 2 plus 2 is 2 plus 2, or 4. On the graph of g, then, I have the points negative 2, 4, negative 1, 3, 0, 2, 1, 3, and 2, 4. And so when we connect those points, we get the graph of g. And Again, if you have ruler and a straight edge, you should get a straight V-shaped graph through those points. But notice that, just like we confirmed previously, that the graph of G is the graph of F shifted up 2 units. So note that each x value stayed the same, but each y value for those corresponding x values is 2 more than the original point. Now g of x equals f of x minus 3. Again, f of x is absolute value of x, so g of x is absolute value of x minus 3. We have that V-shaped graph for the basic function. Now when we plug in negative 2 into our new function for g, we get absolute value of negative 2 minus 3, which is 2 minus 3, or negative 1. The absolute value of negative 1 minus 3 is 1 minus 3, or negative 2. The absolute value of 0 minus 3 is just negative 3. The absolute value of 1 minus 3 is 1 minus 3, or negative 2. And then the absolute value of 2 minus 3 is 2 minus 3, or negative 1. So we have the order pairs negative 2, negative 1, negative 1, negative 2, 0, negative 3, 1, negative 2, and 2, negative 1, which hopefully you had already recognized that by the virtue of this type of function, the result of this graph of g is that it's the graph of f shifted down 3 units, which is what we see in our new graph. So graph of g is the graph of f shifted down 3 units. So the graph of y equals f of x plus or minus k is the graph of y equals f of x shifted up or down k units. So this outside change is affecting the value of y, which is moving things up and down, right? The y is a vertical axis, so we get a vertical shift. So the first property is that of vertical translations. When k is a positive real number, the graph of y equals f of x plus k is a graph of f shifted up k units. So if xy is on the graph of the original function, then the point x, y plus k is on the graph of the transformed function. The graph of y equals f of x minus k is the graph of f shifted down k units. So if the point xy is on the graph of the original function, the point x, y minus k is on the graph of the transformed function.